Kralovo Polska is a prominent engineering and manufacturing company based in the Czech Republic, recognized for its expertise in producing large steel structures, pressure vessels, and heavy industrial components. A key part of their fabrication process is sheet metal rolling, which is carried out using high-performance fabrication plate rolling machines. These machines are critical for shaping thick sheet metal into cylindrical and curved forms, essential for manufacturing reactors, boilers, tanks, and pipeline shells. The company uses FACIN's advanced 4-roll plate bending machines, known for their precision and efficiency in handling heavy-duty sheet metal. These machines include 4 key components: the top roll, which applies downward force to create the bend, the bottom roll, which lifts and clamps the plate to the top roll, and 2 side rolls, which support pre-bending and guide the plate during forming. The 4-roll configuration offers a significant advantage over traditional 3-roll machines by allowing for greater control and continuous rolling without repositioning the material. The rolling process begins with the loading and alignment of the sheet metal on the machine bed. Kralovo Polska typically works with thick carbon or stainless steel plates, ranging from 10 millimeters up to over 100 millimeters in thickness. Once the plate is positioned, the machine's laser alignment systems and side guides ensure the sheet is correctly placed for accurate rolling. The next step is the pre-bending phase, where the machine curves the plate edges before the main rolling begins. Thanks to the FACIN machine's 4-roll design, both ends of the sheet can be pre-bent without removing the plate from the machine, reducing flat zones and improving the overall cylindrical shape. This is followed by the rolling and forming stage, where the top roll applies pressure while the bottom and side rolls adjust to bend the plate into the desired shape. CNC controls automate the roll movements, providing high precision and consistent results across multiple passes. Once the plate reaches the desired curvature, the machine performs a final calibration pass to ensure the shape meets exact specifications. If the component requires multiple layers or thicker profiles, several rolling passes may be performed. After rolling, the product proceeds to welding, inspection, or further forming depending on the final design requirements. Kralovo Polska benefits from several advantages by using FACIN's rolling machines. These include high precision and repeatability, made possible by CNC-controlled movements, time-efficient operations due to integrated pre-bending and rolling, and the capacity to process very thick and wide plates, meeting the demands of large industrial projects. Additionally, the machines are equipped with advanced safety features and automation tools, ensuring a secure and streamlined operation. Their versatility allows for the production of cylindrical, conical, and even elliptical shapes, supporting a wide range of complex designs. By utilizing FACIN's state-of-the-art rolling technology, Kralovo Polska strengthens its capabilities in producing high-quality, large-scale components with tight tolerances. This approach not only reflects the company's technical expertise, but also its commitment to innovation and precision in heavy metal fabrication. Davi, a globally renowned Italian manufacturer of metal forming equipment, plays a pivotal role in the production of wind turbine towers through its advanced 4-roll plate rolling machines, MCB series. One of the prominent applications of this technology is found at CS Wind UK, a leading manufacturer of wind tower sections, where DAVI's equipment enables the efficient and precise forming of large steel plates into tower segments. The MCB machine-controlled bending series from Davy is specially designed for rolling thick, wide plates with exceptional accuracy and repeatability. The 4-roll configuration consists of 1 top roll, 1 bottom roll, and 2 side rolls. The top and bottom rolls work together to clamp the plate securely, while the side rolls perform the bending. This setup allows for a fully automated pre-bending and rolling process, without the need to remove or reposition the material, making it ideal for high-throughput production lines like those at CS Wind. The production process begins with plate loading, where massive steel plates, often over 60 millimeters thick and several meters wide, are fed into the machine. DAVI's feeding tables and side supports assist in aligning the plate accurately. The top and bottom rolls grip the plate, and the side rolls are positioned precisely via hydraulic controls based on parameters input through the CNC interface. The pioneering Davy CNC system calculates the exact roll positions and bending force required for each section of the tower segment. During the pre-bending phase, one side of the plate is curved while the plate remains clamped. Then the plate is rolled forward, and the other side is pre-bent, all while staying within the machine. This is a key benefit of the 4-roll MCB design. It eliminates the need for flipping the plate, thereby increasing safety and efficiency. Once pre-bending is completed, the machine moves into the full rolling stage, gradually forming the plate into a precise cylindrical shape. The continuous rolling action, coupled with real-time CNC corrections, ensures that even large diameter sections are produced with high roundness and minimal flat zones. This is particularly critical for wind turbine towers, where dimensional accuracy and structural integrity are essential for performance and safety. DAVI's 4-roll MCB machines used at CS Wind UK are also equipped with automated feeding systems, hydraulic overhead supports, and outfeed conveyors, all of which streamline handling of the heavy plates and reduce manual intervention. These features significantly boost productivity and reduce cycle times in tower segment production. DAVI's 4-roll plate roll MCB process is central to the efficient and precise manufacturing of wind turbine towers at CS Wind UK. The machine's ability to handle extremely thick and wide plates with fully automated pre-bending and rolling, high accuracy through CNC control, and support for large diameter production makes it an indispensable part of the wind energy supply chain. With DAVI's cutting-edge technology, CS Wind UK can meet the growing demand for renewable energy infrastructure with consistency, quality, and speed. Now we will see a clear picture of how PT Gunung Baha Konstruksi, GBK, expertly manufactures their welded beams, which take the form of familiar WF wide flange, or H-beams. Unlike standard hot-rolled beams formed from a single piece of steel, GBK constructs these beams by precisely joining 3 separate steel plates, 2 flange plates forming the top and bottom horizontal elements, and 1 web plate as the vertical connector. This fabrication method offers significant advantages, particularly the ability to create custom beam dimensions tailored precisely to specific engineering requirements, which might not be available in standard inventories. The production process at GBK is a highly automated and sequential operation. It begins with high-quality structural steel plates, which are cut with extreme precision into the required flange and web components using advanced CNC plasma or oxy-fuel cutting machines. This ensures dimensional accuracy right from the start. Following cutting, these individual plates move to an automatic beam assembly machine. This crucial piece of equipment accurately positions the web plate vertically and the two flange plates horizontally against it, clamping them securely in the exact H configuration. Integrated tack welding units then apply small, temporary welds to hold the assembly together, maintaining its shape for the next critical stage. The heart of GBK's welded beam production lies in the main welding process, typically performed by a large gantry-type automatic submerged arc welding machine. The tacked beam is positioned under this gantry, which houses multiple welding heads, usually two, one for each flange to web joint. Submerged arc welding is the preferred method due to its high deposition rate, deep penetration capabilities, and exceptional weld quality. The arc operates under a protective layer of granular flux, shielding the molten weld pool from atmospheric contamination and resulting in strong, clean welds with minimal spatter. The machine automatically feeds the welding wire and flux as it travels along the beam's length, simultaneously creating the full penetration fillet welds on one side. The beam is then typically flipped, and the process is repeated on the other side to ensure balanced and complete fusion. Due to the intense heat involved in welding, some distortion or bowing of the beam is inevitable. To correct this, the welded beam passes through a hydraulic beam straightening machine. This machine uses powerful, precisely controlled hydraulic rollers to apply pressure to the flanges, carefully bending them back into perfect alignment with the web and removing any overall sweep or camber, ensuring the final beam meets strict geometric tolerances. Finally, the beams are cut to their final specified lengths and may undergo finishing processes like shot blasting for surface cleaning and painting or galvanizing for corrosion protection, depending on the project's needs. Throughout this entire process, rigorous quality control checks, including visual inspection, dimensional verification, and critical non-destructive testing of the welds, are performed to guarantee the structural integrity and reliability of every beam produced by Gunung Baha. In essence, GBK utilizes a sophisticated combination of precision cutting, automated assembly, advanced submerged arc welding technology, and meticulous straightening and quality control procedures. This allows them to efficiently produce high-quality, customizable welded beams that serve as vital structural components in demanding construction and industrial applications throughout Indonesia and beyond. Himash JSC is a prominent name in the metalworking and heavy fabrication industry, particularly known for manufacturing high-pressure vessels, tanks, and industrial components for the energy, chemical, and petrochemical sectors. One of their key specialties lies in the fabrication of dished ends, which serve as curved end caps for cylindrical vessels and play a crucial role in maintaining structural integrity and pressure resistance. To perform this task with precision and consistency, Himash relies on cutting-edge machinery from Thakin SPA, a world-renowned manufacturer of metal forming equipment. The process begins with the dishing stage, where a flat circular steel plate, cut from a larger sheet using flame or plasma cutting machines, is gradually formed into a concave shape. This is done using a Faxon dishing press, which uses a powerful hydraulic ram and a specially shaped die to press the steel into the desired dome-like curve. The machine operates through a multi-pass cycle, where the plate is rotated and pressed repeatedly under precisely controlled pressure. These parameters, such as crown radius, material type, and plate thickness, are programmed via a CNC interface, ensuring accurate and uniform dishing across all sections of the plate. Once the dishing process is complete, the semi-formed end cap is transferred to the flanging machine, another vital piece of Faxon technology. Here, the objective is to form a flange or rim along the outer edge of the dished plate. This flange enables easy welding to cylindrical vessel bodies or attachment to other components. The machine operates with a rotating base and hydraulic forming rolls that bend the edge upwards or outwards as the plate spins. Operators can control the flanging angle, radius, and roll pressure through CNC or manual systems. This stage is particularly sensitive, especially when working with thick materials, as cracking must be avoided through careful adjustment of forming pressure and rotation speed. Both the dishing and flanging machines used at Himash JSC are designed to handle heavy-duty tasks, such as forming plates up to 50 millimeters thick and over 5 meters in diameter. These machines also include real-time monitoring systems for safety and quality assurance. After the forming stages, the dished ends are subjected to grinding, polishing, and non-destructive testing (NDT) to ensure flawless surfaces and structural integrity. Dimensional inspections follow to verify compliance with required specifications and industry standards. Himash JSC's use of Faxon dishing and flanging machines showcases their technological strength in producing high-quality dished ends. Through the integration of hydraulic power, CNC control, and robust forming equipment, they achieve exceptional precision and durability in components critical for pressure vessels. Saarstahl AG is at the forefront of sustainable steel production, pioneering the transition toward green steel through advanced technologies and environmentally conscious processes. One of their most significant innovations lies in replacing traditional blast furnace methods with electric arc furnace (EAF) technology, allowing them to dramatically reduce carbon dioxide emissions. At the heart of Saarstahl's Green Steel initiative is the electric arc furnace, a powerful and efficient melting unit that transforms recycled scrap metal or DRI into molten steel. Unlike blast furnaces, which rely on coke as a reducing agent and generate large quantities of carbon emissions, EAFs use electricity to produce heat through high-energy arcs between graphite electrodes and the metal charge. The furnace is charged from the top with scrap metal, which can include old cars, beams, pipes, and industrial leftovers. The EAF is fitted with 3 graphite electrodes that are lowered into the furnace. When power is applied, an electric arc is formed between the electrodes and the metal, heating the contents to around 1,600 degrees Celsius. Modern EAFs at Saarstahl are equipped with automated charging systems, off-gas cleaning units, and dynamic process control software. These systems manage energy input, monitor chemical composition in real time, and regulate the oxygen and carbon injection to refine the molten steel. The use of renewable electricity sources, such as wind or solar, enables Saarstahl to produce green steel with an exceptionally low carbon footprint. After the EAF process, the molten steel is transferred to a ladle furnace or vacuum degassing station, where secondary metallurgy takes place. Here, operators fine-tune the chemical composition and temperature to meet the exact specifications required by the final product. Alloying elements such as manganese, chromium, or nickel are added, and degassing removes unwanted gases like hydrogen and nitrogen. Advanced sensors and automated stirring systems ensure uniform composition and quality. Once refined, the molten steel is poured into a continuous casting machine, CCM, a highly automated line that solidifies steel into billets, blooms, or near-net shape products. Saarstahl's continuous casters feature mold oscillation, electromagnetic stirring, and automatic taper adjustment for precision casting. The process begins by pouring steel into a water-cooled copper mold, which rapidly solidifies the outer shell while the core remains molten. The strand is gradually withdrawn downward and passes through a secondary cooling zone where water sprays or air mist continues solidification. Cutting torches or hydraulic shears then divide the steel into required lengths. These cast products, such as billets or blooms, are directly sent to rolling mills or intermediate cooling beds, depending on the production route. Through its commitment to sustainable innovation, Saarstahl AG is reshaping the steel industry by adopting electric arc furnace technology and continuous casting systems powered by clean energy. Their ability to turn scrap and DRI into high-quality steel billets and shapes with minimal environmental impact is a testament to the role of automation, advanced metallurgy, and eco-conscious design. Krishna Forge Fitting Corporate is a leading manufacturer of forged pipe fittings, with a strong focus on producing high-quality industrial tees for sectors like oil and gas, petrochemicals, marine, and power generation. The process begins with the selection of high-grade raw materials, such as carbon steel, stainless steel, or alloy steel bars. These are inspected for chemical composition and quality before being cut into billets using hydraulic cutting machines or abrasive saws. The cut billets are then heated in a gas-fired or electric induction furnace to temperatures between 1,100 degrees Celsius and 1,250 degrees Celsius. These furnaces are fitted with temperature control systems and thermocouples to maintain consistent heat, which is essential for a flawless forging process. Once heated, the billets are moved to a closed die forging press, where the basic shape of the T is formed. Hydraulic or mechanical presses, ranging from 500 to 2,000 tons, compress the billet between precision dies, creating the main body and the branch of the T in one seamless operation. Following the initial forging, any excess flash material is removed using hydraulic trimming presses. The forgings then undergo heat treatment, such as normalizing, quenching and tempering, or solution annealing, to enhance mechanical properties like strength and toughness. After heat treatment, the Ts proceed to the CNC machining stage. During machining, CNC lathes, drilling machines, and milling centers are employed to fine-tune dimensions. These machines ensure that bore sizes, beveled ends, and wall thicknesses are consistent and within specified tolerances. Concentricity and alignment between the main bore and the branch outlet are critical and are carefully maintained with advanced CAD/CAM programming and tool monitoring systems. Surface treatment follows, which involves grip blasting or shot blasting to clean the surface and prepare it for final finishing. Depending on the application, the Ts may receive galvanizing, passivation, or electropolishing. Each T is then marked using stamping or laser marking to include vital information such as heat number, size, and material grade for traceability. The final stage includes rigorous inspection and testing. Non-destructive tests like hydrostatic pressure testing, ultrasonic inspection, dye penetrant, and magnetic particle testing are carried out to confirm the structural integrity of each component. Dimensional accuracy is verified using tools such as calipers, profile projectors, and CMMs.